Hello and welcome to Day 87. Today we're talking about one of the core principles driving AI forward, scaling laws.
You've probably heard the idea that to get better AI, you just make everything bigger, right? More data, bigger models, more computers. A kind of brute force approach that seemed to work for a while. But is that really the whole story?
By the end of our time today, you'll see that scaling isn't just about raw size. It's actually a predictable science, one that gives us a clear roadmap for building more powerful AI models.
So what exactly is a scaling law? Well, at its core, it's a predictable relationship. It's a rule that tells us if we increase the key ingredients, data, model size, and compute, we can actually forecast with pretty good accuracy how much better our model is going to get.
Now, to really get the intuition here, look at how we visualize this. On a normal graph, this relationship looks like a messy, complicated curve. It's really hard to predict where it's going. But if you switch to what's called a log-log scale, something kind of magical happens. That curve straightens out into a perfect line. And a straight line, well, that's predictable. That's the secret sauce.
But here's the thing, the field has moved on from just this one simple rule. We've developed a much more sophisticated strategy. Today, AI development is guided by three distinct scaling laws, each for a different phase of a model's life.
Let's start with the first and most foundational one, pre-training scaling. This is the original idea that got everything started.
This law is pretty straightforward. When you increase your training data, your model's parameter count, and the compute you use all at the same time, you get predictable improvements in the model's general abilities. These three things are tied together. A bigger model needs more data to learn from, and training all of that requires a whole lot more compute.
A great way to think about this is like sending the AI to school. This is its foundational education. It's learning broad concepts about the world, language, logic, common sense, from a massive, massive textbook.
Okay, so our model has graduated. Now what? Well, it needs to be useful for a specific job. And that brings us to our second law, post-training scale.
Post-training is all about adapting that general-purpose model. We use a whole toolkit of techniques here, like fine-tuning to specialize it on a certain kind of data, or reinforcement learning from human feedback, RLHF, to align its behavior with what humans actually want. So, if pre-training was general school, you can think of post-training as specialized job training. We're taking that broadly educated model and teaching it the specific skills it needs to be a coder, a legal assistant, or a data analyst.
And the scale of this stage is just staggering. Creating an entire ecosystem of these specialized models can use up to 30 times more compute than the original pre-training did. That's a crucial point. A massive amount of the work happens after that first big training run is over.
And finally, we have the third and newest law, test time scaling. This one is different. It's not about training at all. It's about how the model thinks when you ask it a question.
Think about how you answer questions. If I ask you, what is 2 plus 2, the answer is instant. But if I ask you to develop a business plan, you need to pause, think, and reason through multiple steps. Test time scaling gives models this exact ability to think longer on hard problems. So instead of giving a fast, one-shot answer, the model uses a lot more compute right at that moment to explore different lines of reasoning, break down the problem, and come up with a more thoughtful answer. For a tough query, this can take over 100 times the compute of a simple one. But it's what enables true problem solving. So why does breaking it down into these three laws matter so much? Because understanding this framework is what lets us build AI that can tackle genuinely complex, real-world problems. For example, in healthcare, this long thinking can help predict how a disease will progress. In logistics, it can solve incredibly complex supply chain puzzles. And in software, it can generate and even debug intricate code. These are all things that are just out of reach for a quick, one-shot answer. So, to pull it all together, the idea of scaling has really matured. It's not a brute force recipe anymore. It's a sophisticated strategy for intelligently allocating compute across the model's entire lifecycle. The key takeaway today is this: scaling laws provide a predictable roadmap. They are the engineering principles that allow us to systematically build more capable and more intelligent AI.